好，各位，我们目前测试一下这个语音，各个平台都听得到吧？
醒醒，该上班了。事情是这样的，你周末加班太多，想好好睡一觉，又怕赶。但你在喜临门呼呼 H300床垫上睡得特别香，每次醒来只会感到是全新的一天，不知道现在周几，也不记得之前有没有被叫醒过。现在你醒过来了，那我的问题是，我抛的这枚硬币，你认为是正面的概率是几分之几呢？你可能会说，那肯定是1/2啊，硬币嘛，不是正就是反，你咋丢那不都是1/2吗？确实，不管你睡觉翻几个面，硬币只有2个面，回答1/2合情合理。但现在我们把所有情况都列出来，你有3种情况下会被叫醒：正面周一、反面周一、反面周二。对你来说，这3种情况完全不具有特殊性，可能是任意一个，所以它来自正面的概率是1/3。怎么样？是不是感觉有点意思？这就是我们小学2年级学过的睡美人问题 （Sleeping Beauty Problem），简称 S。乍一听很简单啊，但其实它是一道非常经典的统计学哲学问题。从上世纪末被提出到现在，相关学术论文已经有上百篇了。支持1/2的呢叫 halfer，支持1/3呢叫 thirder，两派人吵得不可开交。目前呢，1/3派略占上风。你支持1/2还是1/3呢？也有人觉得两边都对，只是回答了不同的问题。
嗯，一二三，
回去了，这边听得见吗？
能听到我的直播有声音。
好，没有回音，
一二三，
我这边听没有
这边
回音。
听得见吗？能听到我的直播有声音。
好，没有回音。
听到我的直播有声音。
好，没有回音。
听到我的直播有声音。有回音。
有回音是你那边是不是开了外放？
我不知道怎么判断是回音还是什么呀？
没有，你其他设备，你如果不用手机同时开外放，应该没有回音。现在就没有回音。
啥叫用手机开外放啊？我现在是用
就是你
电脑进的会，电
啊，对，
脑
用电
说的话。
脑进的会，但是你手机在那个会议里嘛，你手机会把那个回音重复。就你如果手机在那个看那个直播的话，
我手机，嗯
问一下他们，现在应该没有回音了吧？那个周老师，对，没有回音了。OK，
嗯，对，那我还有一个问题就是，直播的时候，需要有往公屏上打什么东西吗？这你有没有提
不需要，
前给我？
不需要，他们自己有准备。
哦，好，
好，所以就保持目前这个情况，然后我们等华为老师进来，然后4点钟直接开始播就可以了。保持目前这个情况，然后等华为老师。
好，我知道了，那是我这边，我搞清楚回音是怎么来的，没事了。
嗯
我说没事了，我知道回音是怎么来的。
，OK OK，嗯。
嗯嗯。
Okay. Hello everyone online. Welcome to the official live stream of the ICME 2026 Low-Bit Large Model Quantization Challenge. And I am Zhao Yun, the host of this live stream. It's a great pleasure to gather with all of you in this live stream. And not only we will bring you a comprehensive interpretation of this, but we also invited technical experts Huang Jing and Cheng Yu, who is responsible for the demonstration of this challenge. They will answer your questions and demonstrate practical operations in the subsequent sessions, helping you to understand the details of the computation more clearly. Next, let's synchronize the agenda of today's live stream. Okay. First, I will explain the background of this challenge. Then Huang Jing and I will introduce the task definition, core rules, and scoring standards of the computation. Next part will be the Cheng Yu to bring a practical demonstration of the baseline, explaining the operation methods step by step based on the official simulation code. And then finally, we will enter the full Q&A session, where we will answer all of your questions one by one. And let me also tell you the interaction rules of the live room. You can ask your questions at any time through the screen, and our staff will collect them in real time. And in the Q&A session, we will give a priority to answering questions related to registration, submission, and computation rules. Other technical questions will be responded to later. Also, everyone is free to ask. All right, let's officially enter the session after the background of this challenge. As the official track of IEEE International Conference on Multimedia and Expo 2026, our ICME Grand Challenge is established to address these some industry pain points, and also has many unique features. So let's welcome Huang Jing to give us an introduction of the Grand Challenge.
Okay, I'll share my screen. Okay, hello everyone, I'm Huang Jing. Now let me briefly introduce this challenge. It's trying to solve one of the biggest challenges in AI today, the compute and the memory war. As the models get larger, the cost of training and deployment is growing very fast. So the key question is, can we keep high model quality while significantly reducing the computation and the memory cost? And this competition is designed exactly to explore that. This challenge focuses on image-to-video and text-to-video generation. There are two research directions. One is quantization-aware training using the high-float 8 format, and the other one is post-training quantization using high-float 4 or MXFP4 format. There is one important constraint. Most of the computation must be done in low precision with only very limited high precision fallback. So essentially, this is a system-level experiment on how far we can push low-bit computation before model quality starts to break. Let's first talk about sub-challenge 1. So this track is mainly about deployment efficiency. The idea is to push the model as far as possible in low precision during inference. Here we are using W4, A4 quantization, which means both the weights and the activation are compressed to 4 bits, and the numerical format used is either IF4 or MXFP4. The base model is 12.2 I2V A14B, and which is a fairly large image-to-video generation model. For evaluation, the dataset used is the OpenS2V5M, and the performance is measured using VBench metrics. since 4-bit quantization is quite aggressive, so the rules give you a little bit flexibility. If you use MXFP4, you are allowed to keep up to 5 layers in high precision. And if you use high F4, you can only keep 2 layers. So this naturally creates a very interesting trade-off. On one hand, more low precision computation gives you better efficiency. But on the other hand, it also increases the risk of accuracy loss. So in the end, the goal is very clear. You want to achieve the best possible generation quality while using the smallest amount of compute and memory. Now let's move to the sub-challenge 2. This track focuses on training efficiency. Here we are using W8A8 quantization-aware training based on the high F8 format. And the key idea is that we are not only quantizing the weights and the activations, but also parts of the attention modules. This is actually quite important because during training, a lot of the cost comes from data movement, not just the computation. By quantizing attention, we are also trying to reduce memory bandwidth pressure. The model used here is 2.1 T2A 14B diffusers, which is a large text-to-video generation model. Another key technique here is something called delayed scaling strategies. Instead of updating scaling factors at every step, the updates are delayed or amortized over multiple steps. This mainly helps reduce computation and the synchronization overhead during training. However, it also introduces some trade-off. Because the scaling factors may lag behind the actual data distribution, it can potentially hurt numerical stability, especially in low precision training. So in practice, it's about balancing efficiency and stability. In terms of accuracy, there is also a strict requirement. The accuracy loss needs to be less than 0.5% compared to the full precision baseline. So essentially, you are being asked to significantly reduce training cost while almost not hurting model quality. Just like the first track, there is a small amount of high precision fallback allowed. Up to 5-layer transformer blocks can remain in high precision, mainly to stabilize the training and prevent divergence. And finally, the organizers recommend a very specific setup. For example, the batch size equals to 1, and the training steps are limited to 1,000. This setup is not arbitrary. It is designed to simulate a resource-constrained training scenario, where you don't have large-scale infrastructure, but still want to fine-tune or adapt the model efficiently. So overall, this track is really testing one core question. How far can we push low precision training before it starts to break model convergence and final accuracy? Finally, I want to briefly highlight a special mini challenge that is available in both tracks. Well, this part is not ranked on the main leaderboard, but it is actually your pathway to the Innovation Award category. For the inference track, you will be working with Pangu 72B 2512, and the goal is to keep the precision loss under 1% across these 5 benchmarks. For the training track, the focus shifts to Open Pangu 1B model. This is a more lightweight, but still quite representative for low precision training research. So whether you are aiming for the main leaderboard or for the Innovation Award, I think the core message of this competition is very clear. The future of AI is not just about building larger and larger models. It's about making our models scalable and deployable. And low precision computation is really one of the key technologies to bridge that gap between high performance and the practical deployment. So that's the quick overview of this challenge and its key details. Thank you.
Okay. After the introduction of the details of the challenge, I can let me to introduce the scoring standards, and I'm going to share my screen. Here, as everyone can see that we have two scoring standards, and first is objective evaluation and subjective evaluation. And the objective evaluation is about 70% of the whole score. And it has the basic baseline. The first, everyone needs to satisfy the baseline requirements, which is we can know that in the challenge one, we have if you use the MXFP4, the full precision must be less than the 1%, and the F4 is the 0.5%. And in sub-challenge 2, and the outliers model must be strictly less than the 0.5%. And also, we also have the V-bench quality measurement. And it is accounting for the 50% of the objective evaluation, and it's also the scores item. V-bench, everyone knows the V-bench is a comprehensive benchmark of the video generation performance. And we are going to use the 6 points of the V-bench in the measurement. And after the meeting, we will put it on our website. And also, the quantitative ratio indicators is accounting for the 20% of the objective evaluation, and the scores is given according to the ranking of the model's quantization performance on the specific benchmark. And we can know the top 10% will get a full score of 20 points, and qualified submission will get 0 points. And then let's look at about the subject evaluation. The subject evaluation, the first of the subject evaluation is authenticity and clarity. It's accounting for 20%. It is reviewed by the college students, which is a volunteer, and we have a double-blind measurement to measure the image quality, dynamic effects, and of the video. And also, we have an innovation. Validation is about accounting for 10% of all the score. It's reviewed by technical experts and divided into 4 scaling dimensions: the algorithm of originality, and half-load native exploration, and generalization of the model. And the last one is engineering value. And at the same time, let's emphasize the submission format of our requirements. All the materials must be packaged into a zip or to compress the package and submitted through the email, which is shown on our website. And the email must include all the quantized model weights and training or inference source code and some script that can make up to the source code reproducibility script and operation instructions. So to the above are the core rules, and time comes to the Chengyu to bring us a practical demonstration of our baseline. You can focus on the on the method of the simulation code. If you have any questions, you can record them in the bullet screen first, and we will enter the Q&A session after the demonstration.
Okay.
Yeah, let me share my screen. Okay, hello everyone. So here I'm going to demonstrate the code compilation and the function calls of the quantization simulation tool. Okay, so it's actually two tools but share the same API interface, so I combine them together. The overview of this toolbox, including the HighFloat 8 and HighFloat 4 repository. So the purpose of each one is to simulate the HighFloat 8 and the HighFloat 4 format on both GPUs and NPUs. In addition, the HighFloat 4 repository, including more low-bit relatives such as the MXFP4 and other 4 bits format. If you are interested, you can dive into and try them by yourself. Okay, so the primary usage of this tool is actually you can just define the Q type, which infer to the quantization type. For HighFloat 8, you just set the high F8, and for HighFloat 4, you just set the high FX4, plus by the quant float function, so which later I will introduce in detail. So the backend supports both CUDA and ASIN NPU. So you can choose which library you want to use and on your machine. Okay, so the extra functions is including the autograd functions wrapper, which enables you to train the model or fine-tune the model based on some gradient surpass. And the second one is the Q-linear wrapper, which is a higher level wrapper that transfer the normal linear layer from PyTorch to the quantized linear function. Okay, so here is the overview demo video of the how to run, how to build, and how to call the functions. Okay, so in the first place, you just run the build.sh. So for NPU, it should be build NPU ops.sh. Okay, and after you press the enter, it will automatically go to the compilation process. And after the compilation, you can see the SO library is generated in your CUSRC folder. So maybe wait for more time. So this will finish. Okay, there will be a lot of warnings because the PyTorch library, some warnings itself. Okay, so after you finish the compilation, you will see the SO library is generated to the local directory. So the arrow, the right hand side is empty, means that it's installed in the local path. And then you run the test files. We include 3 levels of test files. The first one is the quantization function. So after you call it, you can see the difference between the NumPy, Golden, and PyTorch and the kernel. Each of them, the difference is 0. Okay, and then you can run the gradient function. Okay, so here is still for different data type. Okay, and you can see all the difference are 0. Okay, so then after that you can run the gradient test with the autograd function. So here we have 2 testings. So one is the forward pass, the difference should be 0, and also the backward pass, it should be 0 as well. And yeah, last but not least, so you can run the linear function. Okay, so it replaced the normal PyTorch linear layer to the quantized linear layer. So you can see these layers are replaced from the normal linear to the specified linear layer. After that, we will run the numerical test, where the loss is very small and the data type should be B float 16. And here it passes the test, means that the quantized linear representation is success. Okay. So yeah, after this short demo video, so we will see the workflow of this repository. So the first one is the reference math, which is implemented in the NumPy format. So you can see the NumPy file, which includes the two F8, means the two float point number 8-bit.py. And also we have the float 4, which is the high float 4, NVFP4, and others format. So we have the NumPy Golden for these formats. And then we have the framework wrapper, including the quantized type and the quantized tensor, quantized linear. And also we have the wrapper function of the replace linear functions to help you to just replace the quantized linear by one click. Okay. And then go to the backend kernels. So for NPU, we have the quantized NPU library, and for the CUDA, we have quantized CUDA library, and including implemented by the SNC as well as the CUDA language. Okay. After that, we call the validation, which is just showed in the demo video. We have high float 8 validation, high float 4 validation, and some quant function validation and linear replacement function. Okay, so the typical usage is listed here. So you just run it step by step. And which is should be noted is that the dimension, if you use the quantization, the dimension should be the inner axis in the matmod. For example, if you run the matmod in the MK matmod by KN, so it should quantize the K axis instead of the M or N. Okay, so this is the quantization point you need to take note. Okay, so for the API, the very basic one is the quant dequant float. So this actually is a core simulator helper used by the library to bridging your PyTorch API to the kernel API. So this applies the quantized and dequantized path, which applies a numerical simulation of the quantization process. So because we don't have the exact hardware of the high float 8 and high float 4, so we do this numerical simulation by using this function. Okay, and then we have two implementations. As we showed here in the screenshot, we have a NumPy implementation, which is on the CPU, and PyTorch implementation, which are using the very basic PyTorch functions, and also the kernel, which you implemented using the SNC or CUDA. Okay, and so it implies different levels of optimization. So of course, the CPU one is the very low performance, and the kernel one is the highest performance. So you can choose which one to use in your scenario. The advantage of using each one is that NumPy or PyTorch, you can investigate what happens in each step, and if you are interested, you can dig into them step by step. Okay. So the second level is the AutoGrad wrapper. So for the AutoGrad wrapper, it enables you the ability to train or fine-tune the model. So we actually have the forward and backward. So you can see the backward is just surpass the gradient from the output to the input. So you don't need too much like implementation of the gradient function, because we just want to simulate the error or the loss caused by the quantization in the forward process. And you can just keep your backward or gradient as it is. Okay. And next one is the Q-linear, which is the quantized linear layer for the implementation. And here the core difference is the backward function of this linear layer. So for the backward, you can see that here we implement the quantized gradient function. So if you are interested, or this is just for research purpose, if you want like investigate the how we can use the low bit training or the low bit functionalities in the backward process, you can just enable the gradient output. If for the numerical simulation, you just disable it and run it as the normal linear function. Okay. So the last one is the shortcut of the linear replacement. So we provide a shortcut function called replace linear. So you pass in the model and the quantized type, and you just, as just mentioned, you can just pass the quant grad as false. So after that, it will scan the model, each layer of the model, and replace the linear layer with the Q linear. So you don't need to replace them in the the model script or the model py file. So it's just a shortcut for your quality of life. Okay. So the appendix is how to install the CAN package. So we tested this library on the CAN 8.3, but for the newer version of CAN package, it may success, but make sure that your accuracy or your difference should be 0.0. Okay. So we test it on 8.3.RC2, and you just download the toolkit and install based on your own hardware or CPU structure. So after you install the CAN package, you just run the set install bash to set up your environment. And after that, you can run the build npm op.sh. So for the CUDA, we have tested on CUDA 11 and CUDA 12. So they both can normally run the CUDA side kernel. So yeah, that is the environment constraint for these two packages. Okay, and thank you. That should be all of my part.
Okay, thanks for the introduction of the demo. And now, after understanding the demo of all the codes, and whatever cares most about must be the score rule. Must be care about the time nodes. So let me to share my screen. Here, we can see that registration is from February 10th to the April 10th, and the deadline is April 10th. This is only registration window for the challenge, and you need to complete the registration through the registration form on the official website. And there is an alternative link available. You can ask questions related to the restriction in the bullet screen, or just email us. And the second is the final submission phase. It's from the March 15th to the April 30th. If you need to submit all the participating materials within the window, so no supplementary submission will be accepted afterwards. And the third is the review and verification. It's from April 15th to the May 8th. The organizing committee will review all the submitted results and verify the reproducibility of the results, which is an important link for winner rewards. And we will announce our final results before May 12th. So we will officially announce the list of winners of all the awards, and you can pay attention to the announcement of the official website and the competition of the Git code or just the ICME website. And the final manuscript, all the awarded team or the recommended team that who want to publish a paper which is in the SME, everyone need to submit the technical report before the May the 15th, and you can download the tag template or the word template in the SEME website, and we need to we need to have and after attended the meeting, and you can your report can be published in the IEEE. So let's come to the Q&A Q&A part. And is anyone have any questions? Let me see. Okay, we can see that okay. Let's see the first question. It comes to the baseline requirement about average loads. So we know that in VBench we have a lot of a lot of sorry. Yeah, many math. Oh, sorry. Yeah. How to define the average loads of the VBench? Can Huang Jing to answer this question?
Is it the
Sorry, I have echo here.
is it the question about the baseline requirement about the average loss define and the calculation?
Yeah.
Well, the requirement used to evaluate we use the V benchmarks metrics using the imaging quality, aesthetic quality, overall consistency, and subject consistency. And one more is the motion smoothness. And to calculate the average loss, we evaluate every metric and calculate the average of the metrics.
Okay. Let's see, it's another question. Oh, it's another question for Chongyu. So, what it means that which GPU or NPU is fit for this grand challenge? Is there any restrictions of the NPU or GPU?
So for the GPU, we don't restrict as long as it supports the bfloat 16. And for NPU, we only have the kernels for the 910B and 910C.
Okay. And it's a good question, and we know that not every participants can have uh, the GPU or NPU, which is the SN910B or 910C. So every GPU or NPU from NVIDIA is also allowed to use in this grand challenge. And let's see another question about it's about the mix. It's about W4A4. Which means that can it use the mix the data type, which means that use HEF4 and MXFP4 together to in one in one block. So can anyone answer this one?
I think the requirement is to use either MX FP4 or high F4, cannot mix them. And because
Okay.
if you quantize the weights or the activation, first of all, you cannot mix them, quantize them differently, use different formats. And we prefer you to test the numerical format, apply them to the whole model to test the to make sure that this numerical format is available to the model.
Okay, so we cannot use mix the tab, and you can only use one have 4 or MXFP4. And another thing. Oh, it's a question about if someone wants to change the sub challenge, change sub challenge 1 to 2 or to attend the mini challenge, how to operate. To me, I can answer this question is about that you can just to submit another report that you can have a new team and just which means you can withdraw your former submission. Okay, and next question is about how many videos are recommended to be tested on Vbench. Can Huangjing answer this question? Okay. We know that, okay, I found that. I found that we have renewed our test data set on the website, and we can see that which is in out on the have 4 and have 8. It's about 1,000 videos in each of the tests each of the testing data set. Yeah. So is this a good answer that you know? Okay. So what's waiting for the questions? What about to talking about some something about this challenge? That what do you recommend? Think what is the most difficult part of this challenge? That Cheng, can you just let's answer it, or let's talk about this challenge. Just waiting for more questions.
So this is quite an open question. So
Yeah.
the most difficult part of this challenge is actually because we have several tracks. So for the inference is that actually I think is the insertion point of the quantization in the model. So you know the large language model is actually a very big system, and they have many layers and different types of layers. So where you insert the quantization is a very tricky and very it's a very precise thing you need to do. Okay, and for the fine-tune task is actually you need to find the correct way of fine-tuning the model by considering the quantization loss. Yes, so I think for different track they have different difficulties, and that's what's based on my understanding that was my answer. Yeah. Okay.
Yeah, I was told that someone think that the sub challenge, the mini challenge, another sub challenge, the mini challenge it seems more harder than the sub challenge, which means which means that the text to only the text the large language model is harder than the T2V or the I2V model. The mini challenge is more harder. Is that right?
Yeah.
Okay. You mean the mini challenge is more harder, but we only have the we only have the innovation award for the mini challenge. Okay. So let's. So what so for the two experts, Huang Jing and Cheng Yu, what do you recommend for give some recommends to these other participants?
Well, for me, my recommendation is that at the track, which one to choose is depend on the participants what they are good at. And because actually for inference and the training, they are in the different scope. The quantization is not quite the same. And for me, I do more on the inference quantization. And I know that especially for the 4-bit quantization, there are many tricks on the many tricks to keep the model quality. And mostly you need to carefully design the quantization and you need to figure out which layers are most sensitive to the quantization. And sometimes you need some algorithms to calibrate the model to achieve a better accuracy. Yeah.
Okay, right. So, Chongyu, can you give some recommend for the participants?
So actually, I think for me, the requirement of the training or fine tuning is has higher requirement for the participants because they need to put more resources or hardware into this kind of model tuning process. So actually, these two tracks they have different it's a different test for the participants. So one is how you control the training data or the training techniques. And another inference task is actually how you can monitor the quantization loss of each layer and how you can control the error accumulation by introducing the quantization into the model. So these are actually two different ways if you consider it in detail. Yeah. So based on what you are good at, you can pick the one you are more confident at. Yes.
Okay, good. So for now, that is about 15 minutes from the about the live. So if there is no more questions, I will come to an end of this section of this live. So the Q&A session today is coming to an end. I believe that through today's live stream, you have a comprehensive understanding of the background, tax rules, and scoring standards, and baseline operation of the SME 2026 low-bit large model quantization challenge. And we have solved some questions at this stage. So everyone knows that as the official track of the SAME 2026, this challenge not only provides some rewards, but more importantly, provides a platform for communication and innovation for researchers and developers in the field of low-weight quantization of large models. We hope that you can actively participate, spark more technical sparks in this competition, and make more research results with the practical value. So finally, thank Huangjing and Chengyu for their wonderful demonstration, and thank all the friends online for watching and interacting. And this comes to the end of the official live. So see you at the competition in Bangkok. Bye.